Thank you all so much for joining us here today for another one of our TCU alumni webinars. We're really excited today to be joined by the new Dean of College of Science and Engineering, Dr. Michael Kruger. Dean Kruger is a physicist that is coming to us from the University of South Dakota. Before that, he did his undergrad at the State University of New York at Stony Brook, did his graduate school at UCLA, and has previously taught at the Australian National University, which is pretty cool, and the University of Missouri, Kansas City. And he has been with us for about a year now, and we're just really excited to have him on campus. And we are really excited today to talk about the physics of a curveball. My name is Ryan Tiglis. I work here in the TCU alumni office, and we're just really excited to get going, talk a little baseball, talk a little physics. Everybody loves the marriage of those two things. And with that, I'll turn it over to you, Dean Kruger. Like I mentioned right before we logged on, is that there is a Q&A section at the bottom of your Zoom screen. If you have any questions throughout the webinar, throw them in. We'll have a Q&A section at the end of the call.
Ryan, thank you for the introduction. It's a pleasure to be here, and I want to thank you, everyone here, for joining me. It's just a real pleasure to talk with you about physics, the physics behind curveballs, and I appreciate you sharing your lunch hour with me. All right, let's jump in. I have a few preliminaries before we start. I'll just talk a little bit about where my interest in sports physics came from, and it was by accident from my perspective a little bit. About 20 years ago, someone from the National Federation of High School Sports Associations, which is to high school sports what the NCAA is to college sports, they approached me and asked if I'd be able to help the baseball rules committee, their baseball rules committee, make some sense out of the non-wooden bats. They were really hot at the time, outperforming wooden bats, and there were lots of questions and concerns. This is a relationship that's continued for the last 20 years as they continue to be interested in the intersection of science, technology, sports, and there are other areas that intersect. Law and business also intersect those areas often. And the more I worked with them, the more my interest in sports physics grew, and I thought others would find that interesting as well. So I created a course that went from non-existing to regularly getting well over 100 students in each semester, and that was a lot of fun. Cover all sorts of sports, all sorts of physics. In the bottom left, you see a young woman doing the high jump. It's a funny way we do high jumps these days, and there's a good physics reason behind it. I worked so much and done so much physics of sports that a colleague of mine and I wrote a book on it, the physics in sports, and which is now out of print, but it was a lot of fun to do and covered a lot of good sports. Okay, let's pivot. I use to be of more interest. I call this talk curveball physics, but really it's about breaking balls, which are any balls that are thrown with spin, and the spin causes a deviation from the path that they would otherwise go. The origins are way back around the 1870s. A little bit hazy who first threw a breaking ball, a curveball, but sometime in the 1870s. First seen in college ball in 1876. So Charles Eliot is not a name that most people know, but we feel his effects. Charles Eliot was president of Harvard for many years and a visionary. Modern American universities owe the way they look to Charles Eliot, president of Harvard University. The various aspects of the university are due to him, including things like the credit hour. So he was a true educational visionary. When he learned about the curveball, this is what he's reportedly said. I tell you, it's time to call halt when the boasted progress in athletics is in the direction of fraud and deceit. So Dr. Eliot was a true visionary in education and maybe wasn't looking so far into the future in baseball. You can be a visionary in one area and not in another. So curveballs, breaking balls have been around for a long time. And in 1941, Life magazine conducted a study looking at curveballs, breaking balls, And at the end of the study, they came to the wrong conclusion. They missed literally 8-inch deflections and concluded that the deviations were were illusions and not real. So it's a little bit of a storied history of when the physics of curveballs initially, or at least an early study, concluded that the breaking balls simply didn't break. That's wrong. Okay, now let's take a look. Let me make a couple of definitions. Let's take a look at fastballs and curveballs, and we'll start with. Let me point out where let me get a laser pointer on. So over to the left-hand side, we have the pitcher, and all the way on the right-hand side, we have the batter. That's the orientation we'll use here. Let's take a look. We'll start off with the left, a fastball. And we usually don't think of a fastball as breaking, but they do in a sense, to the extent that a fastball has spin. And in this case, from our vantage point, the spin is clockwise. We'll study why. That's the point of this talk, but we'll study why that a fastball which has backspin will appear to rise. That is, it doesn't actually rise, but it doesn't drop as quickly as you'd expect it to. And humans have a good intuition for how quickly things should fall when they're thrown. A curveball is just the opposite, where a curveball has a spin that's in this orientation, it's clockwise, and it drops. It falls more quickly than you would expect it to. Bottom line, and what we're going to study here, is that spin will alter a ball's trajectory. We won't talk about the knuckleball. That came along for a free ride in this picture. So we need to review some. So we talked briefly about fastballs and curveballs. So we know what they are. Now we need some physics in order to understand why a fastball rises and why a curveball drops. So if you've had first-year physics, you may have come across Newton's 3 laws of motion. We only need one law, Newton's 3rd law of motion. Every action, and by action we mean force, every action, every force has an equal and opposite reaction. So in your mind's eye, consider these 2 skaters. We have a woman on the left and a man on the right, and they're on ice so that we don't have to worry about friction at all. And imagine, if you will, and you can think this through, and you know what will happen. If the woman pushes against the man, what happens to the man? He gets pushed away, right? And he moves off to the right. There was a force on him and he moved to the right. And that seems easy enough to understand. But if you think about it, you know, if you were that woman and you gave a push, you know what would happen to you. You would go to the left. Why did you go to the left? You went to the left because even though the man didn't go like this to push against you, forces always come in pairs. So if you pushed on him, he pushed on you. Every action, every force, to every force, there's an equal and opposite force. Newton's 3rd law of motion. It's not complicated. That's all there is. Okay, so we write that down, we put it in our mind, we hold on to Newton's 3rd law of motion. We will need it for understanding curveball physics. There's something, so now we need we need to know a couple of more bits of physics, and then we'll put them all together. We need to know a little known effect called the COANDA effect. The COANDA effect, you've seen this. You've seen this in action, but maybe not have paid attention to it. COANDA effect is simply stated is that fluids, gases or liquids, will follow surfaces. So here we have an example of the COANDA effect, something very close to the COANDA effect in action. So water is coming out of a faucet. You see a thin stream of water, and It's just going straight down. If there was no spoon involved, it would continue to keep going straight down. It comes up to the spoon, and then what does it do? It kind of sticks to the spoon, following the spoon's surface. Okay, we've seen that, and perhaps nothing remarkable. Take a look as a by the way. Look what happens when the water leaves the surface of the spoon. It does not immediately go straight down, right? It continues going off to the left. Okay, let's tuck that away in our mind for a little bit. So now let's marry the COANDA effect, which is fluids follow surfaces, with what we just covered, with Newton's third law of motion, action and reaction. Action and reaction. So let's think about this again. Water is coming straight down before it interacts, before it comes near the spoon, going straight down. When it leaves the spoon, it's going down, but it's also going to the left. The water is now going to the left when it wasn't before. There must have been a force applied to the water. Why else would it go to the left? That force applied to the water is just like when the woman pushed against the man. The woman pushed against the man went sliding backwards. We don't need to worry about why, but clearly something interacted with the water. And there are only two things in this picture, a spoon and the water. The spoon interacted with the water. The spoon pushed the water, pulled the water to the left. That's the COANDA effect. Newton's third law, action and reaction. For every action, there's an equal and opposite reaction. If the spoon pulled the water to the left, strangely enough, the water must be applying a force on the spoon to the right. COANDA effect and Newton's third law is telling us that if you were to very carefully measure the force on the spoon before water was touching it, there'd be no left-right force on it. But if you were to very carefully measure the force on the spoon after the water is just going straight down, right? Going straight down from the faucet, there would be a small force pulling the spoon to the right. Let's take a look at the COANDA effect and Newton's third law in action. Here's a picture of a fellow with a piece of paper. I understand you can see me, hopefully, but I can't see myself, so I don't know if you can see me, what I'm doing. I'm just have a piece of paper just like this gentleman does in the picture. So I am a professor of physics. I have to ask questions in the lecture, but fortunately, no one is going to be graded on them. So here's my question for you. Let me draw a pen. Okay, so we've got, what I'd like to know is, I'd like you to think about for a moment or two, if he's blowing air that goes straight out, that's supposed to be straight. Does it keep going straight out? So that's guess A. That's answer A. Does it follow the surface of the paper? That would be guess B. Does it get repelled by the paper? And that would be guess C. So I'll give you a few moments, not very long, just to think about this. Does it follow the surface? A is it just goes straight. That's the way he's blowing the air. B is it somehow interacts with the paper. It follows the path of the paper. And C is it is repelled by the paper. Well, we've thought about it long enough. We know the COANDA effect. The COANDA effect is that it's an observation that we see that air will follow the surface. So it'll look like this. So that's the COANDA effect. Now let me ask you this. Will the paper move? That's the first question. The second part, or the first part of the question, and the second part, if it does move, which way? This is a great question. if you can answer this, you fully absorbed what we discussed before. And this is stuff that you've not thought of before. So let me walk you through it, and you can test yourself, see if you got it right. Well, when the air first came out of his mouth, it was going straight, right? It was unambiguously going this way. If there was no paper there, that's the way it would have gone. But you see that because of the COANDA effect, air is going down. There must have been a force on the air pushing it down. The only objects here are the air and the paper. So if there's a force, if the air is being forced downward, and we know from Newton's third law, if a reaction has an equal and opposite reaction, there must be a force on the paper, must be pushing it up. This seems unbelievable, right? You got to try it for yourself. So I have a sheet of paper already. I'm going to hold it up and I'm going to blow the air. I'm going to blow straight across and we'll see what happens. Physics is an experimental science, as all sciences. And it's something, and when we come up with ideas, right, they need to be tested against reality. If they agree with reality, it gives more credence to the ideas. And if they disagree with reality, it tells us we need to go back to the drawing board. So we need to run this experiment to see if what I'm saying makes sense and agrees with nature. So I blow straight, and yet it makes the paper go up. Seems completely unintuitive, and yet that's how Mother Nature works. All right. So we did try it. So we learned what can happen with just the COANDA effect and Newton's third law when they marry. Now let's add spin. Hopefully with spin, we'll then fully understand breaking balls, curveballs, etc. So here, it doesn't matter what the ball is. This happens to be a basketball. I was able to get this image, so that's what we'll use. If you'd prefer, think of a baseball here. So in this image, the basketball is spinning clockwise, and we have 4 streams of air that are in such a way that you can see those streams of air. The topmost stream. Let me get the laser pointer back. Oh, sorry. I don't know what happened. Okay. Both the topmost stream and the bottommost stream, the lowest stream, are so far from the basketball, they don't interact with the basketball. We can ignore them. Let's take a look at the top stream. Now the top stream is going from right to left. Now think about the basketball. If the basketball is spinning clockwise, the top of the basketball is moving rapidly to the right, moving rapidly in the direction opposite to the air. The air has very little time to interact with the basketball and almost doesn't even notice the basketball, just goes, kind of dissipates. Certainly doesn't seem to go either up or down. Now let's take a look at the bottom stream of air. Again, the bottom stream of air is going from right to the left. But when we're on the bottom of, if you're on the surface of the basketball and when you're at the bottom part, the basketball is moving in the same direction, this way, from right to left, as the stream of air. A particle of air and the basketball surface on the bottom will hover around each other for a longer period of time, longer time than the top of the basketball and the air would. During this time, they can interact longer, and you see the results. You see the COANDA effect much more. That is, the air on the bottom, because it gets to spend more time around the basketball, tends to follow the basketball surface more. The air on the bottom is, after it leaves, after it passes by the basketball, there's a deflection upward. The air at the top is not deflected, not either upward nor downward. So on the whole, when the basketball passes, when the air passes by this basketball, there's a net force on the air, upwards. This is good. I hope this doesn't get boring for you. Invoking Newton's third law, right? If there's a force on the air going in upward direction, and the only other object that we see is a basketball, that air must also be applying a force in the downward direction on the basketball. This is known as the Magnus force. This is what causes all breaking balls, all spinning balls to deviate from the path that you would expect them to travel. And we'll keep exploring this. Here I've substituted the basketball for a drawing of a baseball. And again, we have, this particular spin would be a curveball, where the spin, again, the baseball is thrown from the left to the right. The spin is clockwise. Just as in the basketball, the air that's rushing past it at the top is going from right to left. And the surface of the baseball up here is traveling with the speed of the baseball, but more speed on top of that because of its rotation. On the other hand, and so it passes by the air, or the air passes by the top, by any part of the top very quickly. On the other hand, the surface at the bottom of the baseball is traveling to the right with the speed of that the baseball was thrown, minus, need to take into the fact that it's rotating and going from the right to the left. So the air on the bottom spends more time interacting with the surface. The air on the bottom is deviated much more than the air at the top. Again, the air at the bottom moves upward. The air at the top, not so much. And the net force on the air is going up. The net force on the ball is going down. Exactly what we saw before, exactly what we saw before. Let's take a look at, so we say a curveball drops. All thrown balls drop. They all hit the ground eventually. When we say a curveball drops, we mean it drops, and we refer to that, it's dropping more than we expect it to just by gravity alone. Now let's spend a little time with the fastball, which has backspin. It's everything I said for the curveball, but backwards or in reverse. Right? You can see the surface at the top surface is to some extent going the same direction as the air, causes the air to deviate, going downward. The air at the bottom sees a surface that's going very quickly to the right. Not just the speed of the ball, but the speed of the ball plus the spin. So it's not deviated nearly as much. There's a net force on the air going downward, and therefore a net force on the ball going upward. To some extent, like the ball acts a bit like an airplane wing. And there is upward lift. Not enough upward lift to prevent it from hitting the ground. Certainly that's not the case, but there is upward lift. And because of that upward lift, we say that a baseball or fastball rises. It doesn't really rise. Gravity still wins. Gravity wins at every step of the way. And a fastball never rises, never goes up. On the other hand, it drops much more slowly than you would expect it to. And again, humans, we have a really good intuition for how things fall. And it can be a little disorienting when objects don't fall the way they should or the way we expect them to. Okay, pictorially, let's just take a look. A curveball versus a fastball. Pictorially, you'd see the top graph is the trajectory of a curveball. You see how much it drops. And by the way, you see a lot of drop at the end. That's another physics lesson, why the drop happens so much of the drop is at the end. it's too much to delve into right now. And I'd have to think about how to talk about that without boring you with equations. And in contrast to the curveball, you see the way a fastball drops. Not nearly as quickly as you'd expect it to. And right, and a pitcher would use this to their advantage to an attempt to fool the batter so they miss. Let's take a look at a video of Clayton Kershaw, if I can make it work. Just a few pitches. I tried to get it, I'm sorry, I tried to get it in slow motion where it's even more clear, but hopefully you can get a sense that the ball is dropping more quickly, especially when you look at the end, near the end, right, shortly before it's over the home plate, just how quickly the ball is dropping. Really impressive. So that's reasonably close to home. Let's go even closer to home with our own Tommy VAIL. Let's see if I can get this to work.
Playing deep over at first base, as is Taylor over at third. Tommy VAIL delivers a little breaking ball at sneak.
So Tommy VAIL's curveball, I think that was at 76 miles per hour and 2,400 RPM. Okay.
Ship.
Please don't worry. Although I have an equation up, we're not going to do any calculations, but I think this equation for telling you where the Magnus force, remember the Magnus force is the force responsible for making curveball curve. It's that extra force that pushing the ball down. Depends on four things for the most part. The density of air, the ball diameter to the cubed, that's ball diameter times ball diameters times ball diameter, times the spin rate, times the speed. So for baseball, spin rates are maybe around 2,000 RPM. Speeds vary, of course, as do spin rates, but 85 miles an hour seems reasonable. Okay, so air density is ball diameter cubed, spin rate, and speed. To put in writing what I said about ball diameter cubed is shorthand for ball diameter times ball diameter times ball diameter. So I'm not going to calculate anything, just let's think about this. If you double the air density, you double the Magnus force. It'd be very thick atmosphere to go through, but you would double the Magnus force. If you double the spin rate, let's hop over there, you double the Magnus force. If you double the speed, you double the Magnus force. If you double the ball diameter, well, you'd have a doubling here, oh, and I forgot this first one, and doubling there. So that would be 2 times 2 times 2. The Magnus force would increase by a factor of 8. So if increase the ball diameter, Magnus force grows very quickly. I got a little ahead of myself by jumping into that. What I should have mentioned is in baseball, you can get Magnus forces of about 1/3 of gravity. Pretty significant, right? Certainly non-trivial force and plenty of force to move the ball enough so that a batter can't make contact. But going back to my comment about the ball diameter being cubed, right? If you double the size of a baseball and kept everything else constant, this would be 8 times larger. And the Magnus force would be bigger than gravity. So a soccer ball isn't a big baseball, that's for sure. But it really is a lot bigger than a baseball filled with air. It's very different, but it has a large diameter. And if this equation is correct, we expect soccer balls to be able to experience huge Magnus forces. And so that curvature of a basketball, a kicked and spun basketball would be more obvious, more impressive even than a breaking ball. So I have a couple of clips of that. So again, remember, there was a movie back a few years ago, Bend It Like Beckham. Here we do have David Beckham kicking. This is a better view. We have a couple of more kicks. Here it is in slow motion. Check this out. Pay close attention. This kick is not going anywhere near the goal, nowhere near. And look at all that curvature, all that curving, and look at all that curving that happens near the end. All right, let's keep going. Okay, I made a few videos in advance of demos of a demo that we can do at home. In this first video, which came out reasonably good, I realize I'm saying curveball. Probably I mean a slider, which would be a ball that deviates for the most part left or right due to spin. So I don't really mean curveball in this video. Okay, let's take a look at it. Hi, what we'd like to do now is create a demonstration of a curveball of the Magnus effect, Magnus force in action. Maybe the best thing to do would be to actually throw a curveball or kick a soccer ball and bend it like Beckham. I can do neither of those things, so they wouldn't make for good demonstrations. Instead, we'll make a demonstration that I can do and you could do as well. So to start off with, take two 6 to 8 ounce paper cups. These happen to be 6 ounces, and put them together bottom side against one another. You'll take a bit of sticky tape. Use that to wrap around to connect the 2 cups together. So let me start it. It is out of the field of view, but I've started it and I'm just going to finish up. Doesn't have to be particularly pretty. It just has to keep the cups together. There's only one other item we need, which is a medium-sized rubber band. We'll take that rubber band and we'll cut it. Oops, cut it in 2. And now we have a stretchy string. Fantastic. Let's take that stretchy string. Let's take the one end of the rubber band and put it up against the center where the 2 cups meet. And what we're going to do is we're going to stretch and wrap. Stretch and wrap. I think we can do one more. Stretch and wrap. And now we have something that's vaguely like a bow and arrow, where the cups are like the arrow. And remember, I want to pull the arrow towards my chest. Pull the cups towards your chest, not this way. Because if you let go this way, the cups will hit you, right? So pull the cups towards your chest, and I'm going to aim for the door. Now think about what happens if there was no Magnus effect and I had reasonably good aim. I expect the cups to more or less go towards the door. Right? Well, we know about the Magnus effect, and we expect the cups, because when they're launched, we expect them to deviate from that straight line, from the straight line that they would normally go. So let's see if this works. Okay, 3, 2, 1. Indeed, quite a lot of curve. So a fantastic demonstration of the Magnus effect, of how to throw a curveball, how to bend it like Beckham, something you can do even without any training. You can even do it inside your office or your home. Okay, let's, we'll take, oops, I didn't want to do that. Okay, so there was a lot of talk and a lot of showing you how to build this demo. To give you an opportunity to look at the last bit, which is maybe the most interesting part. I just cut it down and you can watch it. We'll watch it again, maybe just twice more. It's pretty short. It's not going straight. Yeah. All right. So that was maybe a slider. And let's take a look let's do this one more time. I already have my paper cups with this rubber band strung around it. And this time, let's simulate a fastball where we have topspin. And let's take a look at how this will work. So I'll aim again for the door. 3, 2, 1. So there you saw you saw my fastball, and fastball thrown with when it's really just 2 paper cups really does initially beat out gravity. That really did rise. Fastball thrown as a fastball, a real fastball, clearly doesn't do that. Okay, I have one more pitch to show you, but I needed to leave my office to make this happen. This is called curveball physics. So let's do a curveball or a demo of a curveball. I have the paper cups already preloaded and ready to launch. I needed to move to a different space. My office wasn't right for demoing the curveball, at least not on a video. So I'm going to walk to the other end and I'm going to send this curveball your way. You recall, for a curveball, the top of the ball, the top of the paper cups will be spinning, going in the same direction that the ball is traveling. Okay, so in this case, the top of the paper cups will be moving in towards you. I will also send the paper cups at a slight upward angle. You'll be able to see it a little bit longer this way. Okay, so what happened? This is okay. So I think what we found is a nice demo. If you want to show this to anyone, make the demo. It's super cheap, it's super fast, and it just keeps working. Right? It's easy to get to work. You know, something. And I mentioned in one of the videos that consider the cups like an arrow. I'm not sure why. I have them right here. I'm not sure why this is the case, but a lot of people, hopefully this is in the field of view. I can't see myself. A lot of people like to do this, right? And then when they do that, and let go of the cups, it's going to go and hit them in the chest. Doesn't hurt. It's just a couple of paper cups. It also doesn't demonstrate the breaking balls at all. So enjoy that. And I hope you enjoy that demo. Okay. I've got a few other things I want to tell you before we go to Q&A. Let me see if I can. I can't talk. I don't think it's possible for me to talk and not brag a bit about the College of Science and Engineering here at TCU. The College of Science and Engineering is composed of 11 departments, from biology and chemistry to psychology and ranch management. We have six institutes: Institute of Behavioral Research, Environmental Studies, etc. We're the second largest college at TCU. Our students are among the very best, and our alumni remain unbelievably committed to TCU, to their college, to the TCU as a whole, to the College of Science and Engineering, and to their departments. If I can, just a few numbers. We are the second largest college. When I said our students are awesome, I can back it up. 1 in 3 honor students are in the College of Science and Engineering. Our faculty, over the top, engaged with our students. I can back that up with metrics, one of them being that over 40% of our undergraduates are engaged in research. We have 39 programs of study, and pretty much no matter what someone is interested in, we've got it covered. And one other number that's worthy of note, and an impressive one at that, is our students get into medical school at around twice the national average. We're in the news, and this would be an entirely different talk and a long one. If I just talked about how the College of Science and Engineering is in the news, for example, leading in conservation, whether it's helping the horned lizard make a comeback, or whether it's saving rhinos in Africa. We're in the news, leading difficult conversations, talking about what's going on in Ukraine, or talking to children, or talking to victims of human trafficking. I mentioned earlier how impressive our students and our faculty are. There's one metric that I just got to experience. It was last Friday. We have something called the Student Research Symposium, where our students highlight, where they fill up this building, Tucker. And this last Friday, we had 122 undergraduates and 50 graduate students filling Tucker with poster sessions, talking about the research they've done over the last year. If you're in town when this happens, I recommend being there. It is impressive. Okay, enough of my advertisement. Let's get back to curveball physics. Let me summarize it. See if you've got it in your mind. The force that causes balls to break is called the Magnus force. Has a name. What causes the Magnus force? It's the result of three things. One is the ball spinning. Another is the COANDA effect. And don't forget Newton's third law. Spinning balls, COANDA effect, and Newton's third law combine. When you combine them, we give it a new name. We call it the Magnus force. Now, if you already with those two, you can impress your friends. If you want to go the full 9 yards, you'd even remember the formula. It goes as the air density, the ball diameter cubed, the spin rate, and the speed. Okay, this wouldn't be a complete lecture if there wasn't at least a quiz at the end for you. So imagine something quite silly, but imagine astronauts fully suited up because they're on the moon. Right, the moon is desolate, nothing living there except for the astronauts. There's no air, right? No atmosphere, which is why the sky is black. It doesn't have a beautiful blue sky like we have. But they have a bit of time on their hands, and they drop the bases around on the lunar surface, and they want to play ball. And so the astronaut that's the pitcher throws a curveball. The astronaut who's pitching really had been a pitcher in this scenario, and he's got a curveball that he wants to throw. Here's the question. Could the astronaut actually throw a curveball? Would the ball drop faster than you'd expect it to drop on the moon? Right. And let me get my pen back. Well, let's go back to the formula for the Magnus force. The formula for the Magnus force is air density, ball diameter cubed, spin rate, and speed. So we've got a ball diameter. It's the baseball like we've always had. He can spin it, and he can throw it fast. So we've got everything except there is no air on the moon, no air density. There is nothing for the ball to push on and therefore to get pushed by. You've got no COANDA effect because there is no air. There's no fluid for the ball to pass through. Sorry, no breaking balls on the moon. All right, I think that ends it for us. And let me
we're gonna move into a little bit of Q&A real quick.
Okay.
And just want to thank everybody for submitting all their questions. We got quite a few of them, so we're only gonna be able to get to a few. But we're really excited that so many people contributed to this webinar. Let's start with a baseball question, Dean Kruger.
Yes.
Anyone that's watched baseball recently knows that hitters are talking about launch angle more than anything else. Can you tell us a little bit the basic physics behind a launch angle, why that might be beneficial for a hitter to increase their launch angle. I understand that's more of a geometry question, but thought you might be able to provide some context.
Yeah, so I think the launch angle, I think it's with the with StatCast and all of the I'll work up to the answer. So we've got StatCast, I think, in every park now, and with what is it, something like 17, 20 cameras, I can't remember what, looking at the ball, looking at the pitcher, looking at every player on the field. What we've seen is, just empirically, what we've seen is launch angle is really important for, launch angle is correlated with success, right? So if you hit the ball at a launch angle of less than 10 degrees, probably going to be a ground ball, you're probably going to get out. Between 10 and 25 degrees, you get a line drive. If you go, the sweet spot, I think, is like, I don't remember now, like 25 to 35 degrees is the sweet spot. If you hit the ball 25 to 35 degrees, if you hit it hard enough, so the exit velocity is fast enough, you've got a home run. So empirically, we see that you get on base much more often if you hit between 25, hit with a launch angle of between 25 and 35 degrees. To continue on, to build on your question, right? Pitchers also are interested in the launch angle, right? So they have what an average launch angle against is what you'll use for a pitcher, right? And so pitchers want an average launch angle against to be lower, right? Just one ground, ideally one ground ball after another, assuming they don't get strikeouts. So empirically, we find launch angle sweet spots, 25 to 35 degrees. It's not always been the conventional wisdom. But remember, conventional wisdom didn't have data, just had intuition, which wasn't always right.
Awesome. Thank you for elaborating on that. Going a little further, and this also might not fall under physics specifically, it might be more of a, I don't know what it would fall under, but virtually all MLB ballparks now have a humidor to store their baseballs. Can you elaborate on the science of keeping the ball in a humidor prior to being thrown? Yeah,
sure. So I think I need to think back. I think I've got this right. So before the introduction of humidors, it was noted that some parks, they were home run parks. There were a lot of home runs, and it took a while to figure this out. But what people eventually figured out, and I'm really impressed that they figured this out. What they eventually figured out is that in areas where the humidity is low, let's say Arizona, Colorado, in areas where the humidity is low, right, that actually impacts those are the areas where the parks are, we get a lot of home runs. And there's a correlation, because if the humidity is low, over time, the balls themselves have lower water content, right? Whatever moisture they may have goes out into the atmosphere. And as a result, the balls are drier. And it turns out that they're bouncier, not Super Bowl bouncy, but they are bouncier than their humid cousins. And so the dry balls, they bounce off the bat more quickly, or with more energy more quickly. In the parlance of physics and also now baseball, their coefficient of restitution, right? Or in base, we'll often just call it the COR. The COR of the ball is much higher. So to kind of have equity across the parks, so you know what you're going to get. The balls are stored, and I forget I'm sorry, I just don't remember the regulations. What people do. They're stored in humidors, constant temperature, constant humidity, and they stay in there for a long time until they equilibrate with to whatever so they all have the same temperature when they start out and the same humidity. And during the course of play, yeah, the temperature will change, but the moisture content of the ball will not change appreciably during play.
Great. So we've got a bunch of versions of this question. and so I'm going to kind of combine them and then ask a question that's related.
Okay.
So people are asking about like laces on a baseball. Would the smoothness of a ball matter? How do you curve a ping pong ball? Things of that nature.
Sure.
And so my question is, combining all those things, could you in theory throw a curveball with a lacrosse ball? Because I understand with the ping pong ball, it's a lot lighter. There's other things at play there, but lacrosse ball is relatively heavy. Could you, when it has no ridges, could you throw a curveball with it?
You could, yeah, absolutely. So you can have a perfectly smooth surface and a curveball could be thrown. But remember, like you're talking about a lacrosse ball. Let's go back for a baseball. The Magnus force is something like a third of the force of gravity. So imagine you were to take a baseball. So let's forget about any other ball. We'll just forget about a lacrosse ball, forget about a ping pong ball. Let's just take a baseball and carefully unstitch it. Take the cork and yarn out from it and replace it with lead, and then stitch it up carefully. So to the outside world, to the air that's passing by it, it looks just like a baseball. It's got the same look of a baseball. And now a pitcher tries to throw a curveball with it. It's a lot denser, so because it's lead and not yarn and cork. So it's harder on the pitcher, to be sure. But let's say he can get it going, get the ball going at the same speed and the same rate of spin as a baseball. That's unimaginable in real life, but in your mind, you can imagine he does that. The Magnus force would be exactly the same as for an undoctored baseball, but it wouldn't be as impressive, right? Because the force of gravity. You know what? I'm taking us down a wrong path, right? I don't. Half the time when I'm asked questions that I haven't thought about at all before, I can go down a path and then at the end I realize I've led us down a long path that I didn't need to. Bottom line is the Magnus force would be unchanged. You can throw with a smooth ball, definitely a Magnus force. With a ping pong ball, maybe not quite as noticeable because you've got, I think drag probably wins the day for a ping pong ball, but certainly there would be a Magnus force on any ball. So sorry about that.
No, that was great. You answered 10 questions right there.
Okay.
So I've got a few other questions just to help introduce you more to our alumni. You're relatively new to TCU. Can you talk about what drew you to us?
Oh, sure. I think I alluded to some of that when I bragged about the college. TCU as a whole is just an outstanding place. Excellent numbers, right? Yeah, it's ranking in US News and World Report. Its first year retention, the quality of the students that come here, all first rate. The faculty that embody the teacher-scholar model. They are world-renowned researchers who are outstanding educators and bring their undergraduates, not just the graduate students, but bring the undergraduates into the lab. We have over-the-top committed alumni who are actively engaged in helping to ensure the success of our students. When you add amazing students, fantastic faculty and staff, and stunning alumni, the confluence of these results in the TCU magic. So yeah, I was drawn because of that.
All right, well, I've got one more question for you before we wrap up. It's common knowledge on campus that the College of Science and Engineering has a wind tunnel on campus. Can you talk about that for a minute or two here before we wrap things up?
Absolutely. So the wind tunnel it's awesome. It's not just it's for undergraduate and graduate student education. I think the maximum wind speeds I don't remember exactly. I think something like 200 miles per hour. The opening is relatively small, so it's not like you can put a car in there, but you can put baseballs in there. You can put models of cars, and they've looked at. I know some of the experiments. They were looking at curveballs. They've looked at knuckleballs, and what did they find? I think I'm going to get the number a bit off, but I want to say between something like 70 miles per hour, a knuckleball thrown at about 70 miles per hour is going to have the most erratic behavior. So that 70 to 80, that's the sweet spot for throwing a knuckleball. Anyway, it's a great resource for our undergraduates.
All right. Thank you so much for joining us here today. Thank you to everybody that tuned in. Just a quick reminder, if you haven't in a little while, please update your contact information with the alumni office at alumni.tcu.edu. If you're not receiving the emails for the events going on in the area, that's probably why. So please go in, update information, and thank you so much for joining us here today. Everyone have a great rest of your day, and go Frogs.